Nathan here from State Audio Works, usually in Joburg, but in the Eastern Cape at the moment. And the purpose of these webinars again is for instructing, inspiring, and giving insight into what we do. Ross, over to you.
Right, so for those that don't know me, my name is Ross, coming from wet and miserable KZN, and we're going to speak about some input chain and manipulation of audio signals today. So we have, let's see what some of the topics are. We're going to cover is mics, phasing and polarity, cabling, DI boxes, the mixing console, EQ, dynamics buses, and log versus digital. So there's quite a bit of stuff to get through, so I think let's just get cracking on. Right, so we're going to start with mics. We're talking about a transducer that converts energy from one form to another, namely acoustical energy, which are sound waves, into electrical energy, which is the audio signal. Different types of mics have different ways of converting energy, but they all have one thing in common, which is the diaphragm. And this is a thin piece of material such as paper, plastic, or aluminum that vibrates when it's struck by sound waves. The diaphragm vibrates, causing other components to vibrate, and those vibrations are converted into electrical current, which then becomes the audio signal. So we talk about two main types of mics, dynamic mics and condenser mics. So let's get into dynamic mics and what they're all about. These are very versatile, ideal for general use, normally quite sturdy and resilient to rough handling. Also better suited to handling high volumes from certain instruments and amplifiers. And let's just take a look at how a dynamic mic works. So it uses a wire coil and a magnet to create an audio signal. So if you look at the cross section here, when a magnet is moved near a coil of wire, an electrical current is generated in the wire, which I'm sure most of us know. So the diaphragm is attached to the coil. When the diaphragm vibrates in response to incoming sound waves, the coil moves backwards and forwards past the magnet. This creates a current in the coil, which is channeled from the microphone along the wires. Condenser mics, these tend to be more sensitive and responsive than dynamic mics. So they're quite well suited to capturing subtle nuances in sound. Not that ideal for high volume work, as their sensitivity makes them prone to overloading and distortion, those types of things. So condenser means capacitor, which is an electronic component that stores energy in the form of an electrostatic field. So if we look at the cross section into how it works, condenser mics have two plates with a voltage between them. Now, one of these plates is made of very light material and acts as the diaphragm. When struck by sound waves coming in, the diaphragm vibrates, changing the distance between the two plates and therefore changing the capacitance. And when the plates are close together, capacitance increases and a charge occurs. And when they are further apart, capacitance decreases and a discharge current occurs. A voltage is required across the capacitor for this to work, and that's why we use phantom power typically, but in some mics you can use a battery as well, but we don't see that many of those today. Right, so let's get into polar patterns. So every microphone has a property known as directionality. This describes a microphone's sensitivity to sound from various directions. Some mics pick up sound equally from all directions, others only one direction or a particular combination of directions. Typically, we talk about three main categories. So omnidirectional. These pick up sound evenly from all directions. So a use case, I guess, is capturing ambient noise or where sound is coming from many directions, maybe in recording an orchestra or something like that. Next up, we have cardioid. So the sound is picked up mostly from the front. So if you have a look here at the pattern, you can see what we mean when we say cardioid, and you can see lesser extent from the sides. So in a use case, because it emphasizes sound from the direction the mic is pointed, it leaves a little bit of latitude for mic movement and ambient noise. So good for handhelds, for vocalists, and some rejection from the rear as well. So good with on-stage monitors and that type of thing. Hypercardioid is an exaggerated version of the cardioid pattern, very directional. So you can see it eliminates quite a bit more from the sides. There is it can have increased sensitivity directly to the rear, and you'll often see hypercardioids being called shotgun mics as well. So those very directional with a lot of rejection from anywhere other than where you are pointing the microphone itself. Bidirectional uses a figure-of-8 pattern, picks up sound equally from two opposite directions. Again, in a use case could be maybe if you're recording an interview with two people sitting opposite each other, or again in an orchestra setting, perhaps. So frequency response refers to the way a microphone responds to different frequencies. Every mic has a characteristic that some frequencies are exaggerated, others are attenuated. For example, a frequency response which favors higher frequencies means that the resulting audio output will sound more trebly than the original sound. Now, an ideal flat frequency response means that the mic is equally sensitive to all frequencies. So in this, no frequencies would be exaggerated or reduced. So this line on the chart would be flat. Response is not possible. And even the best flat response mics will have some deviation. So that line will never be flat. The next thing we're going to discuss in mics is proximity effect, is the exaggeration of low frequency sounds in a directional microphone when the mic is located very near the sound source. So if you start maybe with a vocal from a small distance from the sound source and move closer to the sound source, you'll notice a rising bass response from the mic as you move it closer. So at this point, I'm going to ask my friends in Namibia if they can do a practical demonstration of this so everyone understands better what we're talking about.
Okay, cool. So with the proximity effect, just the added bass as you get closer to the sound source. So if I speak very closely, you see these people who very wrongly cup the microphone, which means that, well, we'll get into that later. But basically just the lower bass response when you're really close to the microphone, and as you move away, can you still hear me? But it's a very trebly sound. So the further you move away, the less bass the mic will pick up. I hope that explains it a bit. You get the radio presenters that speak very lowly into the microphone like this. So Ross, are we good with that?
We are, thank you.
Cool.
In a practical sense, proximity effect, I'm sure a lot of guys here are house of worship guys or front of house guys that have had to deal with these issues. I know there's one particular church that I do quite a lot of work for and have in the past, and they have a youth pastor that insists on preaching with a handheld, and he holds it literally at his belt. So it causes a world of problems. And every time I'm there, I have to reiterate, please, I can't have you using the microphone that way. And I think for a lot of engineers, it's a stressful job as it is, with a lot of responsibility. And I think it's important that engineers with the right attitude can tell pastors or preachers or anyone what they need. You don't have to just sit and suffer in silence just because someone wants to use a microphone down at their waist, because you know, they think it's fine for you to produce the best audio in the room, or maybe for your broadcast, or for whatever it is. That's just far less than ideal. So we need to speak up and say, this is what I need and this is why. And I think it's totally within your rights to do that. Moving on to mic placement. So mic placement can greatly affect the tone and amplitude of the source. And then on axis and off axis also have a huge effect. And again, this is something I see a lot of in churches, or when I've done any training with some of the sound guys. The most basic thing you should do every time you come to your band practice or your Sunday morning or whatever it is just to check that your mics are pointing in the right direction. Because I know that a lot of guys don't do this, and they, you know, the kick mic ends up just lying inside, pointing towards the shell, or snare mics are facing, you know, I don't know, your cheap mic stand has just, the clip has just drooped and it's not firing at all at what you're trying to capture. And you're just wondering why things are sounding so distant or so roomy, and it's just a really bad starting point. So for me, I think it's critical. You always check all your drum mics, guitar amp mics, anything where you're trying to capture a specific part of an instrument should be checked every single time you're gonna mix anything, really. So if you look at this diagram, you'll see we've got a cone driver here showing a microphone on axis straight, flash on, and at an angle off axis. So changing the axis of the microphone alters the impact, amplitude, and frequency response of the sound being recorded or amplified. On axis, we can see the microphone is aligned to the center of the sound source, perpendicular. And because sound takes time to travel, when the mic is placed on axis, the sound wave hits the microphone diaphragm straight on and evenly. But when the mic is off axis, the sound wave hits the leading edge of the diaphragm first and travels across the diaphragm, resulting in less impact, slightly different frequency response. So practically, a microphone placed dead center of a guitar amp speaker, for instance, will have the most impact and the brightest response. The further away from the center we move the mic, the less presence we will hear, and the properties of the sound being captured will change. So again, I'm going to call on Udo in Namibia if he can. He's got a little setup there that he's going to show us how this sounds. So we're going to start straight on at the center of the driver. Udo's going to, I believe, shred some John Mayer. So if we can move out towards the edge of the driver. And then even more extreme case, like you can come right out to the edge. Yeah. Perfect. So there, you could clearly hear when the mic was straight on axis on the center of that driver cone. It was like the brightest response we were getting, and as we moved out to the edge. So again, this is critical. It shows you what changes can be made just from your mic placement. So again, a lot of guys will mark up a guitar amp, head to the desk, push it through the PA, and if they're not getting exactly what they want, it's like instantly go to the EQ and start chopping things to pieces. And I think it's critical on the input phase that we get things as close to how we want them without moving to the EQ section straight away. So that is obviously the guitarist's tone. There's a whole lot involved in that. And then your mic placement. So you could, if it's just too bright and blaring, you don't instantly have to start cutting things out. You can just move the mic out towards the edge of the driver cone and try that. We are going to now move on to phasing and polarity. So phase refers to a waveform's position in degrees of a cycle or time relative to another waveform. So a waveform's phase is 0 until you move it forward or backward from its position. So if you look at this little diagram we got here, these two waveforms are similar, except that waveform 2, the red one, is at lower gain than waveform 1. So they're perfectly in phase with each other and are both of positive polarity. Because they are the same frequency, when you mix these two together, they reinforce each other perfectly. So the end result, this diagram on the right, is a waveform that is of higher amplitude or gain than either waveform 1 or waveform 2 would be on their own. If we have a look, these next two waveforms are also identical, but this time waveform 2 has been phase shifted 180 degrees. So 1/2 cycle forward relative to waveform 1. So if you were to mix these two together, they would cancel each other out. Polarity is a bit of a different thing to phase. Polarity is either a positive or a negative state relative to the original waveform. So a waveform is of positive polarity until you invert or flip the polarity to make it negative. So since polarity can be flipped, you can control that with a switch. Most desks have a polarity switch. A negative polarity version of a waveform will be a mirror image of its positive polarity counterpart. So assuming that everything about the waveforms is the same, which they were in the image we saw just now. So assuming everything's the same, the time, the amplitude, etc., other than their polarity, when you mix them together, they will cancel each other out and you're left with nothing. So the difference between the negative polarity depicted here and the 180 degrees of phase shifted in the image we saw in phase shift is in how we got the waveforms to cancel each other out. So you need to remember that with phase, we are shifting the position of a waveform relative in time. With polarity, we are positioning the waveform as either right side up or upside down relative to its original state. So we are flipping the positive negative orientation, and we're not changing the waveform's position in time. So a practical example of when to use the polarity switch could be on our snare drum. So let's say we have two mics on our snare, top and bottom. So now we've got a single source, which is a snare, with multiple microphones. Because of the different distances of the mics, the incoming signals will be a little off with each other, the timings. So a good way to check if you're getting some phase cancellation would be listen to your top mic and then add your bottom snare mic. You should get a summing of the two audio signals. If the resultant signal is weaker with them both activated, there's some phase cancellation occurring. So engaging the polarity switch, which flips one of the signals 180 degrees, could allow you to get a fuller sound out of the snare. But I think it's worth noting the polarity switch isn't changing the time at all. So merely flipping the positive negative orientation is not an exact science when trying to combat phase cancellation on a snare drum, for instance. So that is the end of our microphone section. We're now going to move on to cabling. In cabling, we're going to talk about two types of audio circuits, namely unbalanced and balanced. So unbalanced. And an audio cable carrying an unbalanced signal uses two wires, signal and ground. This is how, if you look at this picture here, your typical guitar cable is built. For example, a TS guitar cable stands for tip and sleeve. The wire that carries the signal is in the center, and the ground wire surrounds it. And the point of the ground wire surrounding the signal is so that it can shield it from outside interference. However, the ground wire itself acts a bit like an antenna, meaning it will pick up noise along the way. And the longer the cable, the more noise it will pick up. So it's for this reason unbalanced cables are not good for doing long runs. The reason we should use unbalanced cables for instruments such as guitar and keyboard is that these sources produce a loud signal, all the interference the cable picks up is often barely noticeable. And this is contrary to what would happen with the signal of a microphone. So let's move on to balanced cables. Balanced cables have 3 conductors and 3 wires. One of those wires is the ground. The other 2 are responsible for carrying the audio signal. Balanced cables are much less susceptible to picking up noise and are therefore better suited for long runs. So inside a balanced cable, instead of just one signal traveling through the cable, we have 2 identical copies, one in each signal wire, which is the tip and the ring, or the hot and the cold. So one of these is inverted, meaning it is now out of phase with the other signal, so effectively canceling each other out. But when the signal gets to the other end, the polarity of the signal that was out of phase gets flipped around again, and now both signals are back in phase. The most common types of balanced cables are XLR and TRS cables. So XLR cables are typically used with microphones due to the noise cancellation they provide, and they can also carry phantom power, which we spoke about earlier, through pins 2 and 3. So those will be used to power circuitry and condenser mics, DR boxes, and such. So that's XLR. TRS cable stands for tip, ring, and sleeve. The tip and ring are the contact points separated by 2 insulator rings, and the sleeve carries the ground. Now, before we carry on, there's something important to discuss, and that is mic level and line level, as these are going to pop up again. Mic level describes the voltage generated by a microphone when it picks up sound, and this is typically a few thousandths of a volt. So this voltage varies in response to changes in voice level and in the speaker to mic distance, but the signal is still quite small. So mic levels are weak and require a preamplifier to bring it up to a line level. So several devices are used to boost mic levels to line levels. The most common would be your mixing console. Line level is a stronger and more robust signal. It's a standard used by audio processing equipment and common domestic equipment. Line level is approximately 1 volt, or about 1,000 times greater than a mic level signal. Connecting a microphone to a line level input will result in almost no sound at all, because the mic signal is so faint that the line input cannot hear it. Also, connecting a line level source to a mic level input will cause the sound to be loud and distorted, because the line signal is much stronger than what the mic input will accept. So inputs and outputs on many mixers are switchable for either mic or line level operation. DR boxes, this stands for direct injection box. A critical piece of equipment which is very often overlooked, or cheaper options used. Again, I'll often go into a venue or a church, and you'll see these fancy PA systems and mixing consoles and expensive instruments and so on, but then they've got like cheap and nasty DR boxes. So they're basically sacrificing the quality of your entire input chain just to save a small amount of money on a DR box, which doesn't make much sense. DR boxes can be described as the electronic equivalent of a microphone. So just like mics, we get passive DRs like dynamic mics and active DRs like condenser mics. And much like microphones, passive DRs tend to be able to handle greater signal levels. Active DRs tend to have more reach in the sound, but we'll get into that just now. So a DR's primary function is to convert an unbalanced instrument signal to a balanced signal, so that the instrument can be fed to the PA system or recording device or whatever it is. So knowing what we do about balanced and unbalanced cables, the primary advantage of using a DR box versus connecting an instrument directly is noise reduction. The output from a DR box is mic level. And one of the advantages of this, it allows a DR box to operate happily alongside mic signals in a snake or a mult without crosstalk due to one signal being louder than the other. So let's have a chat about active versus passive DRs. Active DRs require a power source. Again, you can use a battery or phantom power from the console. These are generally preferred when using a passive instrument, such as a passive bass. Active DIs employ a buffering circuit or a unity gain amplifier that boosts the signal going to the balanced XLR output. Because of this buffer, active DIs tend to have more reach and makes them a good choice when used with lower output instruments. Passive DIs generally used for higher output devices that have built-in buffers, such as keyboards or active basses. So that would be a bass that, if your bass can take a battery, or electronic percussion, these types of things. Passive DIs are generally used, and passive DIs use a transformer to do the work. To talk about some of the other things we see on DI boxes, most will have a through connector. So this splits the incoming instrument level signal to a separate output. A good use case for the through is to send a bassist sound to his onstage amp. So the setup there would be from his bass into the DI box, from the DI's output to you at front of house, and from the through to his onstage amp. That way you're not having to combat every EQ and volume change the bassist is making on stage. But for a lot of church settings, having a bass on stage or a guitar amp on stage can be a little scary for a FOH engineer, because I'm sure we've all been in a situation where the bassist or guitarist just cranks their onstage amp to a point where you have no control in the room. So obviously it's highly beneficial to have amp rooms to run guitar amps in, or if you don't have that, at the very least, don't fire them straight into the audience from stage. But anyway, that explains how we use the through. We'll also have a pad switch. Most DIs will feature a switchable attenuator called a pad. This can help prevent excessive gain from overloading the circuitry. The circuit decreases incoming signal by a fixed amount. Common amounts are 15 or 20 dB pads. These accommodate the high output of active pickups and unbalanced line level equipment, such as keyboards and other electronic equipment. A ground lift switch is often seen as well on a lot of DIs. So even though DIs do a great job of eliminating external noise in unbalanced line level instrument signals, even balanced audio equipment is susceptible to hum and buzz caused by ground loops. So ground loops, if you look at this image here, it occurs when there's more than one ground connection path between two pieces of equipment. So the duplicate ground paths form the equivalent of a loop antenna, which very efficiently picks up interference. So the ground lift switch on the DI disconnects pin 1 on the XLR jack of the DI box, thus preventing current from flowing between the DI and the mic preamp along the shielding, and thus breaking the ground loop and eliminating this noise. So a lot of the time when you hear hums or buzzes, even if you're not sure if it is a ground loop, it's worth having a stab. Often it can fix your issues if they are ground loop. If it doesn't fix it, then your hum and buzz is not generated by a ground loop. I dedicated a whole slide to this bad boy. So I know there's a lot of people here who are still using these little suckers. You're thinking, it converts jack to XLR. What's the problem? This is you guys right now in the chat. Just having a sneaky look. So I'm not saying that there's never a use for one of these little buggers, because if the keyboard, for instance, that you're using has a balanced output, and you can use this connector as it's simply a plug conversion, really. But if the output is not balanced, you cannot send an unbalanced signal of any real distance at all into your PA system for all of the reasons that we've just discussed. So I guess this is one of those times we can all agree on one thing and say that this is not a DI box. Right, so that's DIs concluded. We're now going to move into the manipulation section, starting with the mixing console. Let's begin with a brief overview of a typical channel strip. We'll use an analog mixer to make things simpler. Right, here's a channel strip of analog console. Let's just go from the top and chat about what these are. your XLR input, where your mic cables connect to the mixer. We've got line input, so where devices with quarter-inch outputs would patch in, although, as we discussed previously, many of these would be converted to balanced XLR. But yeah, that's your line input. In insert, now, insert jacks are used to connect the channel to an external device, such as an effects unit or an EQ or a compressor. So insert cables have 3 connectors, one for the input and output, one that sends the channel output to the external unit's input, and one that returns the sound from the external unit back to the channel. So it's really just a send and return. But something to note, this will obviously only insert that external effect, if that's what we're using, we'll only insert it over this channel, not, you won't be able to use that for multiple channels. So there are other ways to send to effect processes and return them, but we'll cover that just now. We have gain. So gain control, the gain control adjusts the amount of gain applied to the incoming signal. So you will need to adjust this as necessary for different input types such as mic and line. So appropriate gain structure is really a critical factor in making a clean, even mix. It's ideal to have all the signals coming into your console at roughly equivalent levels. So what this does is it ensures that no single input controls the amount of headroom that you will have available. So you'll need to go through each input channel one by one and adjust the gain for the preamp stage so that you aren't getting too little or too much signal into your console. A good practice is to solo the channel, the PFL, and adjust the gain until you get a reading of around 0 dB on your incoming signal. We have a high pass filter, sometimes also called a low cut. On some mixes, this is a fixed value like 80 Hertz or 100 Hertz. Pushing this button will cut frequencies below that value on that channel. Compression, this is one of the dynamic processes, so I'm going to get into this in more detail later. Here's our EQ section. Again, this is a very simplistic version of an EQ section. On simple analog consoles, often you can see you have low, mid, and high here. They will be at a fixed frequency, and all you can do is cut and boost at that fixed frequency. Sometimes you'll see consoles that the mid frequency will be sweepable, so it'll allow you to choose the mid frequency and then boost or cut. But obviously in more advanced consoles or digital consoles, we have much more control of this section, and we will get more into that just now. Aux send, this adjusts the signal level sent to the auxiliary bus. We're going to dive deep into auxes in a second. Pan control allows you to pan the signal from this channel to the left or right of your PA system. Mute on and off allows you to turn the channel on or off. PFL, which stands for pre-fade listen switch. So it sends the channel's pre-fader signal. So before you manipulate this fader, it'll send a signal to your headphone jack so that you can monitor the direct signal that you have coming into this channel. And the fader, which adjusts the channel's output level and allows you to balance the levels between the channels of your mixer. Let's move on to some terms that you'll see or that you'll hear guys talking about. What is a bus? A bus is a way to send or route one or more selections of audio to a particular place. So some common buses are auxes, groups, matrices, and your left and right stereo bus. What is an aux? Aux sends can be used for a variety of purposes, such as monitor mixers or sending to signal processors such as effects and compressors. So each aux send enables you to control how much of the specific channel you are sending to the external processor or internal if we're using a digital console. So say we're using an aux for an effect. The typical routing would be from your aux to the effects unit and from the effects unit to a channel, which will act as the return. So in a different way to how we spoke about the insert on the analog desk where that effect unit would only be affecting that single channel. When we route an AUX to an effects unit, from effects unit back to another channel on your desk or an AUX return, any channel that we send to that effect AUX will be processed by the effects unit. If we're using an AUX for a monitor, then we're routing out of the AUX to an amplifier or powered speaker or a headphone amp, for instance. Pre and post, so we can also send AUX as pre and post fader. Pre-fader means that the fader will not affect your AUX sends to the processor. So say we're using an AUX for stage monitors and you're mixing a band, you'll want all of your AUXs to run pre-fader so that you are not affecting the band's monitors every time you're mixing and moving faders. Post-fader means that your fader will affect the signal being sent to your AUX. So an example of when you would use post is, say you're running like a dance show, and you've got monitors on stage, and you want to fade out your front of house music. If your AUX was not on post, if it was on pre, then your PA system would fade out, but your monitors would still be blaring. So you want your monitors to be affected by the fader. So you put it on post, and then when you fade out, the PA fades out as well as your stage monitors. What is a matrix bus? A matrix is similar to an AUX bus. However, we're able to route groups and outputs to a matrix. So AUX is often described as, it's just you're sending inputs to AUXs. So you're sending one or more channels at different volumes to an AUX bus. But with matrix, you're able to send a group of channels, or even your master left and right output bus to the matrix bus. So a common use will be if you have a PA system that's comprised of multiple outputs. So for instance, if you have a church that has a main auditorium, a balcony, a parent's room, and a foyer, to send the same audio that you're hearing in the auditorium PA to these other venues, we use a matrix. So you can route your left-right stereo bus to a matrix and then send that to whatever speaker output you like. And many consoles also offer a channel to matrix as well. So not only, so you can send individual input channels to a matrix too. Another thing to note is that some consoles only allow delay over matrix output. So say you have a venue with delay speakers, for example, to cover the back half of the audience, because sound takes time to travel. You will obviously hear the closest speakers first. So you will need to time delay your second set of speakers so that they're in phase with the rest of your PA system. And on many consoles, you can only do this over the matrix outputs. Equalization. So EQ is the process of changing the balance of different frequency components in an audio signal. So we're essentially boosting or cutting the gain of selected frequencies to enhance our mix. Typical variables we'll find in an EQ section, HPF and LPF is high pass filter and low pass filter. These are used for cleaning up issues at the extreme ends of the spectrum. And I think that's quite self-explanatory. Low pass will allow low frequencies through, high pass high frequencies and cut the lows. A good use case is perhaps on your vocals, set your high pass filter on all of your vocals to maybe 120. So the reason you want to do that is that the human voice is not really generating anything below 120 anyway. Your vocal microphone will likely pass those frequencies through. So there's no reason to leave 4 or 6 mics with all this low end data that the voice is not producing, but the microphone is. You're just leaving it in there to muddy things up. So it's a good practice to clean up any vocal or any input channel that doesn't need these low frequencies, to just use your high pass. Then we will often see a 4 or a 6 band parametric EQ, allowing us to focus on specific low, mid, and high frequencies to boost or cut. So here we have a 4 band. You can see we have a cut here on 30 hertz, 13 dB cut, 13 dB boost on 50, a cut at 370 and a boost at 7K. You'll also see something called Q on your EQ. This is short for quality factor. So Q values of less than 1 will give you a broader EQ curve. values greater than 1 will give you a tighter, more selective boost or cut. So you can see the narrow Q there, that mid boost, and you can see a wide Q on the upper register cut. One thing to take note of when you're boosting or cutting frequencies, you are affecting the overall gain of your signal. So like we spoke about gain structure earlier, it's important to know that it might not be worth spending forever doing this perfect gain structure before you've EQ'd, because once you start boosting and cutting frequencies, you are directly affecting your gain structure. So be sure to keep your gain structure in mind when using EQ. Let's move on to dynamics. So in music, dynamic range describes the difference between the quietest and the loudest volume of an instrument, part, or piece of music. One dynamic processor we use to control this is compression. Compression is the process of lessening the dynamic range between the loudest and quietest parts of an audio signal. This is done by boosting the quieter signals and attenuating the louder signals. So the controls you're often given to set up a compressor are usually threshold. So if you have a look at the image here, you can see the parameters here at the bottom. Threshold, this is how loud the signal has to be before the compression is applied. So nothing will happen if your input signal does not hit the threshold level. The ratio, this is how much compression is applied once we move past threshold. For example, if the compression ratio is set for 6:1, which is very high, the input signal will have to cross the threshold by 6 dBs for the output level to be decreased by 1. Attack, this refers to how quickly the compressor starts to work. The knee sets how the compressor reacts to the signal once the threshold is passed. So hard knee means it clamps the signal straight away. Soft knee means the compression kicks in more gently as the signal goes further past your threshold. And then makeup gain, this will allow you to boost the compressed signal, as often compression attenuates the signal quite significantly. So you want to make up that gain in the end. Another dynamic that we deal with a lot is noise gate. So this is a hardware device or a plugin that can be set to automatically mute the signal during parts of the audio track where the instrument is not being played, and unmute again when it is. So again, these usually have 5 main parameters: threshold, ratio, attack, hold, and release. So here we're looking at a gate. Threshold again is the same, sets a level at which the gate opens. So if your input signal is not hitting your threshold level, that channel is going to stay closed. Once it passes it, the channel will open. The ratio, the balance between the original sound and the gated sound. So for example, instead of using the gate to totally mute the ambience on a vocal track, you can allow some of the ambience to still be heard if that's what you want. The attack, it sets the time it takes for the gate to go from closed to open. The hold state, this allows the gate to be held in an open state after the signal has fallen back below the threshold. So you don't want your gate snapping open and then snapping closed instantly. It's just not going to sound natural at all if you're using this on toms, for instance. A lot of times you'll see guys using gates on drums, and that's just, you don't want all of your drums triggering every time any drum is hit. So you can gate your kick mic or your snare mics closed so that when your drum is playing your cymbals, your kick and snare mics aren't open constantly. You can have them open only when those instruments are hit, but you don't want to do this in a non-musical way, as in snapping open and snapping closed instantly. That's not going to sound natural. The release is you use this to set how long it takes for the gate to go from fully open to fully closed. So fast release quickly cuts off the sound, whereas slower release, it's more like a fade out. Let's chat a little bit about digital versus analog consoles. And here we have a Cell 5 Yamaha and an old Midas Heritage. So digital versus analog is kind of a never-ending discussion and very much a preference-driven one. I also think that application plays a large part in this decision. Some applications just don't warrant a digital console, and other applications simply can't be done on analog anymore. So there are some main factors that differentiate digital and analog. We'll speak about those a little bit. Price. So analog mixes generally cost less than digital, even though nowadays digital can be quite cheap. But I think this price comparison is also a bit misleading, because analog mixes without any outboard gear, such as FX units and compressors, gates, they're fairly limited. So in an analog context, if you wanted to compress 10 channels, you either need 10 separate channels of compression so that you can have different compression settings for each channel, or you have to group a bunch of channels together and compress them all with the same settings. Whereas in a digital console, you have a compressor you can insert over every single channel. Same with effects, gates, and. So the cost comparison is a bit of a loaded one, because to gather all of this outboard gear gets very expensive. Flexibility. Digital consoles are far more flexible than their analog counterparts. So you're able to save entire shows, each with their own channel settings and parameters, recall them instantly. You can program ahead of time and recall your show off of a memory stick. You can store presets for effects, EQs, compression, and load them onto specific channels. In analog, you obviously have to do all of this manually, and you have to edit each parameter manually for each show or application. So you'll often see guys running analog. You'll look at their outboard gear rack, and they've got printed little diagrams showing where each parameter pot should be sitting in case something gets changed or bumped. So not very flexible. Ease of operation. Again, I guess it can be argued that analog consoles are easier to operate, as the layout is generally a lot simpler with just repeated channel strips. Digital consoles can be a lot more complicated with layers of faders. Often the EQ or effects and dynamics, they're not available directly on the surface, requiring you to dig a little deeper. But again, I think this is a preference thing. A lot of guys get really comfortable on digital and can fly on it. So noise. Digital consoles are more resistant to noise from the environment due to their digital transmission of signals, whereas analog consoles are easily affected by noise. And size. So analog consoles, as you can see this one here, can be very bulky and heavy and difficult to transport. I remember when I worked at the Playhouse, we had one of these, and it was an absolute dinosaur. I mean, it was a great desk, but it's moving it around, especially for like a rental staging company, is just not something you want to be doing. And then coupled on top of that, if you have a lot of outboard gear, you need to lug that around as well. Whereas digital consoles can be very compact and quite light by comparison. So they're a lot easier to store and move around. And that brings me to the end of my presentation.
I think you've touched on some really, important points there about, things. So I'm going to post 5 points in the chat over there, which I thought about, of how we can really, measurably define what good sound is. And I think if you have those thoughts in your mind, you can kind of figure out where to apply, these concepts that Ross has spoken about. So the first one there is, obviously low noise. By noise, we mean unwanted sound. So whether that's a buzz or a hum or a bleed from another instrument or whatever, I think, we can really apply what we've learned today about balanced versus unbalanced, or using a DI or not, to try and avoid that sort of stuff, so we can get, a tick box over there of low noise. The second about low distortion, which I think is also quite important, because, if you have a bad gain structure and equipment is operating outside of its design constraints, then you get distortion, which is generally unwanted. I mean, not all distortion is unwanted. If you think about like the sound Udo had on his guitar, or if you have like a really, esoteric valve outboard thing that you want to really drive to get a certain texture. But generally speaking, distortion is a bad thing. And gain structure and understanding the channel strip and all of that is really important. The third one about audibility and intelligibility speaks a lot to mic placement. It all starts there. And we'll talk more about loudspeakers and stuff in the next session. But, this is you have to, if you try and do sound in a church or at an event and you don't meet this function of intelligibility, that means that people couldn't understand what was being said. then I think fundamentally, that's bad. So
Yeah.
yeah, that's quite important. Then about musical balance and SPL, that's a bit more subjective, but yeah, obviously using the tool of the mixing desk to bring these various inputs and components and microphones and DRs together to achieve a good musical balance, and an SPL, so a sound pressure level that's appropriate. So it's not too loud and it's not too soft. But yeah, these
and
are,
it's even.
and even, yeah. So
Yeah,
these are at least what I view as the measurable outcomes of what we're trying to do in terms of achieving good sound. I think it's important to keep
right.
those things in your mind, because a lot of opinion becomes super subjective, especially in
Yeah,
environments that all of us are working in. So
yeah.
I just
I
thought I
think
would add that. Yeah.
on the audibility, intelligibility, I think the more I do sound, I think the input phase is something that guys really don't spend enough time on. Everyone wants to be a wizard on the desk with plugins and inserts coming out their ears and running waves and doing all this fancy stuff, but more than half the job can be done just by having some good communication with your band, for instance, and spending some time on the input chain, like tuning your drums, marking them correctly, work with the guitarist on their tone, marking the amp right. These are not things that you can just, you just slap mics on in 5 minutes and then you're going to go and do this great mix and you're going to fix it all with EQ. It's like, you're not. A lot of time you can really save yourself. And a lot of this also speaks to the responsibility of being an engineer and just having the right attitude and some interpersonal skills, right? To have these discussions that you need to have with the band. You can't just, because for you to do your job properly, these are the type of discussions that you have to have with people.
Yeah, I mean, I think it's an exercise in teamwork to achieve these kind of things in a very effective way. Ultimately, the sound engineer is simply manipulating inputs, not necessarily a miracle worker. So it all starts at the source.
Yes.
I've seen that time and time and time again. But there is a question here from Leon. On an equalizer, the clip setting and gain, how do you balance those? If it keeps on clipping, do you reduce the volume or gain on a channel? I think by equalizer, he means a channel strip. So the clip is not a setting. Clip is an indicator that shows that the input is being electrically overloaded, right? So the gain knob itself is a kind of, let's call it, multiplication knob. So basically it gets the incoming signal from the microphone or the device or source material, whatever, and then the gain is essentially a multiplier of how much voltage to multiply that signal by. This is variable. So as Ross mentioned, if you PFL this channel, you'll see the input coming in on your meter on the console. On most consoles, a lot of consoles have individual meters per channel. So obviously you can use the gain knob to set it up to what we call the nominal operating level in the mixer. So that's what Ross mentioned, 0 dBu, or the first orange light on the meter, more or less. If your gain knob is all the way down and the signal is already clipping, it means there's either the source is outputting a too high a volume, which means you've probably plugged a line level signal into a mic level signal. I think, as Ross explained, microphones output thousands or millionths of volts.
Thousandth, yeah.
So whereas a CD player or a laptop or whatever is outputting, maybe 10 times, 100 times more than that. So yeah, it's important to make sure that you plug line level devices into line level inputs, and obviously then mic level devices into mic level inputs. I think another thing to look at is that a DR box has a button on it called a pad, which basically introduces a fixed level of attenuation. So it drops the signal by a certain fixed, or in some cases variable, amount. But that's usually most relevant on an active DR box, where you have a device with a variable output like a keyboard that could overload the electronics of the DR box itself. It's not necessarily about the mixer, but introducing this pad, can lower the volume to a point where you can avoid that clip.
There's not really a case where your gain is all the way down and you've got heaps of input signal. It's not really ideal.
That's not flexible, because as we know in the church world, when the spirit takes over the playing on stage, and you have nowhere to go with the headroom of the preamps,
Yes.
the mixer
Yeah.
starts to light up like a Christmas tree. And
So that's
then,
just a case where you're asking the player or the keyboard player to just turn their input level down, and you can compensate with some gain, so that you then have some play.
yeah. Leon, I hope
Something
that's
I
answered
didn't.
that question for
I
you.
should have made it clear about the auxes. I did say that pre and post obviously doesn't affect the monitors, but the gain will.
Yeah, of course.
So, if you're moving your fader up and down and you're on pre, the band won't hear those changes. But if you start gaining channels, they will. So
Is Dante network environment, is mic line still relevant? So Dante is obviously a technology that moves digital audio around. And generally speaking, digital audio is measured in one type of value called dB full scale. So the mic line thing relates more or less to the analog side of the signal. So before the signal becomes Dante, it obviously is analog. So we don't plug a network cable into our microphones most of the time. So the mic line thing from a Dante perspective is more or less irrelevant, but obviously there is still in most Dante devices an analog stage where you would be able to, or where of course the gain structure does matter. But yeah, generally speaking, when the audio is already digital, it's past the gain or gain structure stage of the system.
I think something else to mention, Nathan and Ross, is especially with intelligibility, or the total solution is to look at what products, what microphones you use, to use the right tool for the right job. So don't use a lapel mic in a large auditorium with the PA system blaring, halfway on stage and mixing that into. If the pastor wants to hear his voice at the monitor, then a lapel mic will definitely not work. Then rather give him a handheld mic, or there's other examples, but yeah, the right tool for the right job.
A lot of people probably work with volunteers, and working with volunteers is a thing I think, Nathan, you guys chatted about also the other day. And just on the point that Ross made about communication, it's really an important part as a sound guy to communicate with the guys on stage very well. And I think a lot of people miss the importance of a rehearsal. So some people, from my experience, they rock up on a Sunday morning, for instance, and they just want to do a quick sound check and then get going with it without a rehearsal. And I think just on the importance of rehearsals and communicating with the band, and perhaps even thinking about appointing someone in between the sound engineer and the band, like a music director who can do a lot of the communication work for the sound guy. Because like Ross mentioned, running around as a sound guy is such a important but difficult job, because you have to pretty much man the ship, like you in the cockpit, and you have to make this thing fly. And just on that point of communication, to perhaps even think about getting a middle guy, even appointing somebody on stage, one of the musicians or leaders to help with the communication part of things. Because I think a lot of sound guys, they get stuck or they get frustrated with communicating with a band around, for instance, tuning your drum kit, or how your guitar, things like that. Because it really starts with the musician himself. Your input chain. If your guitar isn't tuned, it doesn't matter what you do to your desk, the sound will not be cool. So things like that. I just wanted to mention that as part of this point.
Yeah, an MD really does help, especially if they have some knowledge between obviously being in the band and then also some knowledge about what you need as the mix engineer. But I think it's everyone's responsibility to bridge that gap between the engineer and the band. They shouldn't be just these two separate, just the mix engineer fighting with the band all the time, because you see that a lot. It's really not helpful.
Something else I can add is that it's important to remember that we've got all these tools to our disposal, but it's very important to make sure that it still sounds like music, and use your ears for that. So there's a bit of guidelines and theory, and then there's a few things you need to look at your gain structure. on a vocal, you normally add a high pass filter, but there's no set rule to say that for a male vocal, you cut this frequency always with all mics in all venues at all times. It's important to know that you need to, sound mixing is not, it can't be automated. There's a human factor involved, and that will always be needed to make it sound musical, and then to mix it in and bleed it in. And it's important for people, and I think we're getting more into practical things now, is listen to the type of music that you are mixing. Listen to it at different times, different venues, different systems, and understand what the music is about. And when you're getting to your church setup, and I'm not sure if we're going to touch that later this week, but when you listen to your PA system, play a track that you know very well on a decent set of speakers, to make sure that it actually sounds similar in the venue that you're working than what the CD was produced, or the track that was produced, so that you have a good system to work from, and then trust your ears in that.
Okay, there's another question from Leon. Is the equalizer setting on the mixer applied to the complete output of the mixer to the speakers, and the channel settings for bass, high, and mid is applicable to that device into that channel only? Are these two overriding each other? Which is better, to switch off the equalizer and just use the channel settings? So I think, Leon, your mixer, if I have the question understood correctly, has another equalizer for the output, so like a graphic EQ or something. And obviously, okay, yes. And then the channels obviously have their individual things. So this process that MC just described about listening to a track or whatever could be described as a rudimentary tuning process. So if you listen to the track, for example, and you hear, okay, there's too much low, mid, or bass or highs or whatever in the room, you can use the overall master EQ to adjust for the discrepancies of the loudspeakers or for the room acoustic conditions. But the channel EQs are used predominantly to adjust or to compensate for discrepancies in the input signal. So for example, the proximity effect thing that he showed earlier, if you have too much low mid on a specific channel, you would use the channel EQ to remove that rather than the overall system EQ. So it's not better to switch one off for another, but these are usually used in conjunction. So again, the output EQ is used to tune, if we can use that word, the loudspeakers to the room, and then the channel EQ would be used to compensate for individual input issues or desired effects. By the way, EQ, just another way of viewing it is you could view EQ as basically frequency selectable gain. So we spoke about gain as a multiplication of voltage or whatever, but EQ is doing exactly the same thing, just at a specific frequency. I hope that answers it, Leon. As it sometimes happens that you have better sound when you switch on the equalizer. Yeah, that all depends on what's being set. It's not necessarily a rule of thumb. I've been into some churches where they've applied this crazy smiley face kind of curve, in which case it's always better to turn the equalizer off.
It all depends on what your source signal is like as well. If it's far less than satisfactory, then an EQ is going to help you, right? But that's why it's best to do a lot of the work at the start on the guitarist's amp or on their pedals or whatever the case is. Get that as close to what you want as possible, and then really all your mic is doing is capturing that source. You're not trying to color the sound a million different ways with EQ. I think that's the wrong way to approach it.
Yeah, I've got a good friend who works in a very big church, and they have a multi-million rand audio system there. And you know, he asks me all the time for, you know, advice about, okay, what should I do? What plugin should I use? This and that. But so one Sunday I went to go and mix there, and they have a very nice, big, expensive digital console, and, you know, crazy amounts of processing and stuff that really shouldn't be necessary. And yeah, I just went to the stage and took a look at the mic placements and stuff, and yeah, this was all really, really bad. And so yeah, we just spent some time and listening to the sources and placing the microphones correctly, and, you know, able to flatten most of that processing and you know, in a lot of cases, especially in live sound in general is just a series of compromises that have to be decided on. And I think, you know, you have to decide which compromises you're able to make. But I think, you know, in the case of this guy where the equipment isn't an issue, you know, it was mostly that the equalization and all of these things were applied incorrectly, where the issues could have been fixed with, you know, stuff on the stage in the physical realm. They were seeking complex solutions to, you know, really simple problems. And again, you don't need to have a really big, expensive sound system to achieve good sound. If you term good sound by those 5 factors that we spoke about earlier, I think if we can get there, that will be a good step forward. These are good. Keep the questions coming. Some shops don't have the per device cable marker, e.g. guitar cables, etc. How do you know by default which cable to use for a keyboard or guitar for church use, balanced or unbalanced? Not sure if that makes sense. You do. I don't know if you want to go back to that slide, Ross. But essentially, you know, there isn't a specific cable for a guitar or a specific cable for a keyboard, or in live sound use nowadays, you have 4 predominant types of cables that at least we sell and use in the projects that we do. One is an instrument cable, one is a balanced audio cable, one is a loudspeaker cable, and then more recently, the other one is a network cable. But if we talk about the first 2, the only difference is the amount of cores in the middle. So an instrument cable, as Ross said, it only has 1 conductor that carries the signal and another sort of so-called screen, which is basically a bare wire exposed around the audio conductor. You know, this can carry an unbalanced signal. So by default, most keyboards, guitars, instruments, bass, whatever, if you have a pickup and a violin or whatever, these would have unbalanced outputs. So generally speaking, you can use any cable that has this type of connector with just a tip and a sleeve. So if we talk about the TRS or XLR, so if you can see on the jack, it has 2 black lines over there. So that means it carries a balanced signal. So that has 2 conductors inside the cable and a screen. For carrying balanced signal, you could use any microphone cable. Yeah, as long as the cable is high quality, there isn't much of a difference between these. And by extension, you could even use the 3-wire signal for an unbalanced. You can just link the 2 cores together inside. So, you know, a lot of the time we actually just take to a job 1 type of cable because it can carry both a balanced and an unbalanced signal. About stereo versus mono, this gets, you know, where we cross over from professional audio to consumer equipment. In professional audio, this type of TRS connector here that you see is used for carrying a mono signal. Because of consumers, you have now a 3rd type of device that's using a big TRS jack like this, which is a headphone. Now, as you may know, a headphone is generally stereo because you have 2 ears. So, you know, to keep this on a single cable, the headphone people decided to use this kind of connector. So in this case, the headphone is hot on the tip of the TRS would be the left audio. Ring, for example, would carry right, and then shield would carry ground. So it's a balanced connector, but it's actually carrying 2 unbalanced signals that are driving the headphones. So a lot of times you've tried to plug a mini jack out of your computer, which is just a mini version of this thing. It also has a tip, a ring, and a sleeve, and then into a line level, which is balanced, and you push the fader up and you hear this really weird, crazy sound where the vocals sound like they're cancelled out and there's no low end or anything like that. And if you pull the jack halfway out, you kind of hear the full signal again. And that's basically a very common type of issue where people have, you know, taken a stereo unbalanced signal, so 2 stereo signal was 2 unbalanced signals, and plugged it into a single balanced mono input. You know, which obviously, if you think about what Ross described about phase, you're putting the left channel to the in phase input, the right channel to the out of phase input, and then those are being inverted. So what you're hearing is the result of the left and right signals being cancelled out. So generally speaking, if we just make a practical application, if you were making a PC audio cable.
Correct.
Yeah, if you're making a
the
PC,
2 rings does not mean it's always stereo.
Correct. It means it's in professional audio, it means it's balanced. Yeah. But if you were making a PC audio cable to connect your your laptop to your desk directly, and the run is short enough that you didn't need a DR box or something, you would generally solder up the so-called fan out cable, where you would have the mini TRS on the PC audio side and fanning out to 2 TS connectors, one for left and one for right. So this way it will work.
If I can jump in, Nathan, I think it's
Sure.
important to look at what's on the other end of the cable. Ross also mentioned the insert socket. So that TRS jack is also used for the insert.
Insert,
We've
correct,
got the
yeah.
ground and then
Yeah.
the send and the return as your tip and your ring. So that cable can, yeah, so is it now stereo? Is it balanced? Is it, so it depends on what the cable is connected to, and then just look at it, yeah, from there.
Yeah, I mean, you could use this insert cable if your device is like a, let's say, home theater CD player or something, and it has a big 6 3/4 inch whatever jack on the front of it. You could use this cable to break out from the headphone jack, which is stereo, into 2 unbalanced monos. I think, yeah, it's important to know that just because it has 2 black rings, yeah, it doesn't mean it's stereo. Most of the time, at least in professional audio, it's not stereo, it's actually balanced. Well, in that case, I think that was a very productive session. Thanks, Ross, so much.
Cool.
All
Thanks,
right,
Nathan.
thanks, guys.
Thanks, Udo and MC. For your
Yeah,
help.
thanks, Ross.